Have you ever just stopped and wondered how Kubernetes, this massive, kind of complicated system, actually talks to itself? Well, today we're going on an adventure. Think of it like we're shrinking ourselves down to follow a single data packet as it travels through the entire Kubernetes nervous system. We're going to go from the outside world, deep into the cluster, and all the way back again. Let's pull back the curtain and demystify this magic.
So to really get the problem Kubernetes networking's trying to solve, just picture a super chaotic restaurant kitchen. The cakes, which are our applications or pods, are constantly getting moved, replaced, or maybe they just crash and disappear. If a customer had to know the exact location of their cake at any given second, the whole restaurant would just fall apart, right? This is the core chaos of Kubernetes. Pods are temporary, they come and go. So how on earth do we create a stable way to talk to them?
The solution is actually pretty elegant. You have to stop thinking about it as one big network and instead see it as three different conceptual networks all working together. Each one solves a very specific part of that communication puzzle, and together they bring order to all that chaos. Okay, so first up, you've got the node network. This is easy. It's like the physical street addresses for the different restaurant buildings. It's real, it's stable. Then there's the pod network. Think of this like walkie-talkies for all the staff. This network is actually built for us by a kind of digital plumber, a thing called the CNI plugin, which makes sure every single worker gets their own private channel. And third, we have the service network. This is like a permanent department hotline. You just dial bakery, and it magically connects you to whichever baker is actually working right now, no matter what their personal walkie-talkie channel is. But here's the big secret, the thing that unlocks this entire concept. This service network isn't actually real. I mean, the node and pod networks exist. There are real cables and virtual interfaces. But the service network? Nope. It's just a brilliant illusion, a magic trick that the system performs to make all of our lives easier. And now, we're about to see exactly how that trick is pulled off.
All right, so how does its magic trick actually work? Let's start with the simplest journey you can imagine to see it in action. Let's say a user's request comes in, and everything it needs to do its job is happening inside one single machine, or what Kubernetes calls a node.
Okay, let's get our bearings on this diagram here. The big box, that's our single node, and you can see it has a real physical IP address, 192.168.1.5. Inside, we have two little apps running in their own pods, a web pod and a DB pod. And over on the left, there's an external user who's about to kick this whole thing off. We're going to follow that request on its journey inside this one node. So, the packet's journey starts. First, the user's request hits the node's public IP on a special port, which we call a NodePort. Instantly, a little traffic cop on the node called kube-proxy performs the first magic trick. It grabs that packet and rewrites the destination address to the actual private IP of the web pod. Now we're inside. The web pod needs to talk to the database, right? So it calls that stable but totally fake service IP. And here comes trick number 2. Kube-proxy catches that packet again and rewrites that fake service IP to the real private IP of the DB pod. The entire conversation happens without the packet ever leaving the machine. Pretty cool, huh?
Okay, that was easy enough, mainly because everyone was in the same building. But real clusters are made of many machines. So what happens when our web pod on one machine needs to talk to a DB pod on a completely different machine? This is where things get really, really interesting. So this diagram shows our new, more complex setup. On the left, we've got node A, and that's where our web pod is hanging out. On the right, all the way over on a different physical box is node B, where our DB pod lives. The big challenge now is how do we get a packet to cross that physical network sitting in the middle? And this is where we hit our first major snag. The packet leaves the web pod, and it's addressed to the DB pod's private IP, which you'll notice starts with a 10. But the second that packet hits the physical network switch that connects the two machines, the switch just looks at it and goes, "A 10 address? Never heard of it." And it just drops the packet right on the floor. Game over. So how do we fix this? The solution is a really clever technique called encapsulation. And honestly, it's beautifully simple. We take the original packet, the letter that's addressed from one pod to another, and we just stick it inside a new, bigger envelope. And this new envelope, it's addressed from one node to the other node. And this slide just lays it out perfectly for us. You see the two layers. The inner packet, that's our letter, it keeps its original pod-to-pod addresses. But the outer packet, the envelope, it uses the physical node-to-node addresses that the network switch can actually understand and route. This is the trick that lets our packet cross that physical divide. So here's the really crucial takeaway from this scenario. That whole service magic,
The IP address rewriting trick, it happens entirely on node A, the source machine. By the time the packet gets put in that envelope and sent on its way, it's already addressed to the final real DB pod. So when node B receives the packet, it just unwraps the envelope and sees a direct request for its pod. It has no idea a service was ever even involved. The lie is contained. All right, now for the final boss. We've seen pods talk on the same node. We've seen them talk across different nodes. Now let's trace the full end-to-end trip, all the way from a user's laptop, across the public internet, and deep into a specific pod buried inside our cluster. And this diagram, this puts it all together. Now, it looks a little complex, but we actually have all the pieces now to understand it. Just follow the flow from the user's laptop at the top left. The key thing to notice here is that there are now two totally separate layers of load balancing that have to work together to get the packet where it needs to go. First, you have an external load balancer. This is probably something from your cloud provider, like AWS or Google Cloud. Its only job is to take all that internet traffic and just pick a healthy node to send it to. Simple enough. Once the packet gets inside that node, the external LB's job is totally done. That's when the internal load balancer, our old friend, the kube-proxy traffic cop, takes over to route traffic between the pods. So let's trace it. The user's request hits the public IP of the external load balancer. The LB does layer 1 balancing and picks, say, node A, and forwards the packet to its node port. Kube-proxy on node A takes the handoff and sends it to a local web pod. Now that web pod needs a database, so it calls the database service. This triggers layer 2 balancing. Kube-proxy on node A intercepts that call, flips a coin, and decides to send the traffic to a DB pod on a completely different machine, node C. The packet gets put in an envelope, tunneled over to node C, it gets processed, and the response then travels all the way back to the user. So we followed the packet on its wild ride, but we've been throwing around names like kube-proxy and CNI. Who are the actual software components, the actors on stage that are making all of this networking magic happen? This final map really connects all the dots for us. You can see how the kubelet, which is kind of the manager of the node, kicks everything off. It tells the CNI plugin to create all the network plumbing. You can see kube-proxy sitting there, managing traffic coming into the node, and you have core DNS handling all the name to IP lookups. And then you see the CNI and kube-proxy working together to handle that tricky pod-to-pod traffic between nodes that we just talked about. And here is the ultimate takeaway. The cheat sheet, if you will. The CNI plugin, that's your electrician. It's the plumber that wires up the pod network and builds the tunnels between the nodes. Kube-proxy is the traffic cop. It writes all the rules that make services work. Core DNS is the phone book. It translates those human-friendly service names into those fake but stable service IPs. And the kubelet is the manager on each node, telling everyone else what to do. So if you're ever troubleshooting your cluster networking, these are the culprits you need to go investigate. So, after following that tiny little packet through its incredible journey, from DNS lookups to multiple layers of load balancing and virtual tunnels, you've really seen the beautiful, intricate dance of Kubernetes networking. It really makes you wonder, what part of this whole elaborate system do you think is the most clever invention? And, on the flip side, what might be its single biggest point of failure? Something to think about.